In this video, we'll be talking all about timers. And you're probably used to timers. We use them for all sorts of things. We might use them to turn on and off our taps to water our gardens for us. If we've gone overseas or something like that and we want to make our house look like it's inhabitable, we turn on some timers to turn some lights on and off or something like that. We might set a timer to beep at us when we need to check the roast or something. Timers we use all the time in everyday life. A timer is basically something that has a clock that counts and a condition. When that condition is met, when the timer clock equals that condition, we trigger something, we do something. Now that might be a solenoid to turn off and on our taps. It might be a little relay to turn on off our lights or whatever we have attached to it, our TV. Or it might even be a buzzer that goes beep, 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 beep and tells us to check our food that's in the oven or something like that. Whole lot of different timers. These typical timers, examples that I've just given, are timers that typically operate on a large time scale. We're talking minutes or hours or something like that. The timers within our microcontroller are operating on much smaller time scales. We're talking milliseconds, that sort of time scale. And essentially, this is how they work. We have one register that will be a counter. It will count up and just keep on counting up, and we can control the rate at which it counts and what it counts up to and things like that. We then have other registers that compare themselves to that count register. And if they're equal to it, a trigger condition occurs. Now, that trigger condition might be to generate an interrupt. We've recently talked about interrupts. That trigger condition might be to flip a pin, make a pin go from high to low or low to high or something like that. And basically, we use some registers, we poke some values in those registers to set it all up. And once we've set it up, it just works by itself. We don't need to poll and continually check things over and over and check if our timer value is equal to something. It will just happen for us. It'll do it automatically. So that's one of the beauties of using timers. Now, there are 5 different types of registers that we've got within our timers. So the first one, the TA, and I've written X there because we've got multiple timers within our device. We've got 2 timers, in fact, timer 0 and timer 1. So essentially what we do is we replace that X with timer with 0 or 1, depending whether we're talking about timer 0 or timer 1. So you'll see that notation a fair bit. So our first one is the TA0 or TA1R register. This is our count register. So it's the register that keeps on counting up until it hits a certain value and then it resets again and then keeps on counting up, hits a certain value, resets again, and so on and so forth. Our next one, the TA1 or TA2 CTL control register, is the register that we use to set up the timer and configure how it's all going to operate. We then have 3 capture compare registers. Now we use these normally in comparison mode. You can use them in capture mode if you're trying to time inputs and things into your microcontroller. But basically those ones are the registers that we say, if we want to count up to a value, say FFFF or whatever it happens to be, we put that value, that comparison value, into one of these registers. You'll see later on which register we actually use. We then have a control register for each of these capture compare registers. So we can control them individually and set up how each of them are going to work. So they're the 5 different types of registers within our timers. Now we'll talk about timers specifically within our MSP430. We have 2 16-bit timers, so they can count from 0 to 65,535. They're named timer 0 and timer 1. And basically the timer counts away and it's independent of the CPU in terms of it doesn't require CPU resources to make it count. It's all there and all ready to go. So we don't have to increment it manually or anything. Once we set it going, it goes. We have a clock to the timer and we can control that to fulfill our timing requirements. So we can change the clock and say, let's divide the clock by 8 or let's slow the clock down or whatever it happens to be. We can choose which clock we use within our CPU. Here's a few common things that we actually use timers for. Generating an interrupt at a specific time interval. So if we want to generate an interrupt every 10 milliseconds or 30 milliseconds or 50 milliseconds, whatever it is, we can do this very easily with a timer. Much better than trying to do a delay routine or something like that and generate an interrupt based on that. We can toggle a pin a specific time interval. For example, if we wanted to do pulse width modulation or something like that, we can do that really easily using a timer and really quickly and reliably, and it doesn't use a whole lot of CPU resources to do it. We can also time a particular operation. So if we check a value before and then after an operation, we can work out how long it's been based on how many counts our timer's had. We can use that for inputs as well. Now, our timer's got 3 different modes it can operate in. So we'll briefly describe each of those. It's got up mode, continuous mode, and up-down mode. And it's basically talking about how the clock's controlled and how our counter in is controlled. So for up mode, we use it for accurate timing of a particular period. Now, a period in this case is the TA0 or 1, depending on what time we're using, CCR0 register +1, so +1, one more than the value in that. And basically our timer counts that TA0R register, the timer count register, counts from 0 to whatever's in that TA0 CCR0 register. So it counts from 0 to that and then goes to 0. It counts from 0 to that and then goes to 0, and keeps doing this over and over and over again. Our next configuration is where we're counting, our count register counts from 0 to FFFF, the maximum number you can store as a 16-bit number, and then back to 0 again. So 0 to that, back to 0, 0 to that, back to 0, and it generates an interrupt when it goes from that FFFF to 0. Our final type of timer configuration is the up-down. So it counts up to whatever's in TA0 or 1, CCR0, and then counts back down to 0. And then counts up and then counts down. You notice in this one we can have a longer period because it's double whatever we've got in TA0 or 1, CCR0. And we can generate interrupts when it reaches the top and when it reaches the bottom as well. Separate interrupts are available for each of those.